Hi everyone, my name is Steven Uchtenberg and welcome to my first ever web lecture. So perhaps you've ended up here through YouTube and thought, well yes, I've always wanted to know more about other numerical systems. Or perhaps you're doing a Bachelor of Computer Science at the Delft University of Technology and are now taking the TI 1405 course, Computer Organization. Although that name and number might have already changed, they tend to do that once in a while. To be honest, either method works for me and I'm just glad that you found me. But enough about that now. Today I'm going to talk to you about numbers. You, like me, have probably started learning about numbers by using your fingers. No fingers can be denoted as a 0, 1 can be denoted as a 1, 2 as a 2, 3 as a 3, etc. By the way, I apologize for my lack of drawing skills. As you can see, my fingers, well, they're not really fingers. But this works all fine until we get to the 10. Which, as we can see, is a full set. So we have one full set with 0 left over, making a 1, 0 or 10. 15 is no different. 15 is just one full set with 5 extra, or 10 fingers with 5 left. 38, well, it's just 3 full sets with 8 left over. And addition this way becomes really simple. As you remember from being a child, you could just count your fingers and be done with it. If I were to raise 2 of my fingers and you were to raise 7, in total we would have raised 1, 2, 3, 4, 5, 6, 7, 8, 9 fingers in total. 5 plus 7, well, it's no different. Drawing the fingers, we can see that we get one full set with 2 left over. 1, 2, 12. 12 fingers in total. You may not even have realized this, but in order to do addition, you really need to know a lot of rules. For instance, you need to know that 0 plus 0 equals 0, that 0 plus 1 equals 1, that 0 plus 2 equals 2, etc. There's many rules like this. 1 plus 1 equaling 2, 1 plus 9 equaling 10, 8 plus 8 equals 16, 8 plus 9 equals 17, 9 plus 9 equals 18. But when you do know all these rules, you can basically do any addition you want, because you can apply these rules to larger numbers as well. Say for instance, you have the number 7,319. We want to add to this the number 1,833. All we need to do is go from right to left and apply these simple rules for every pair of digits. So say we start at the right with 9 plus 3. 9 plus 3 we know is 12. So we write down the 2 below and we write down the 1 a step to the left, because the 1 is a full set and needs to be added to the other full sets we have. 1 plus 1 plus 3 equals 5, we write it down and we continue one place to the left. 3 plus 8 equals 11, so again we need to carry over one to the left, we write the other one down, and finally we get 1 plus 7 plus 1 equals 9. And there you have it, 7,319 plus 1,833 equaling 9,152. Something we can easily calculate by just applying the simple rules we know from right to left. This way of counting, using our fingers, having this system wherein we have 10 different numbers, is generally our culture. This is how we do math. But quite recently, we discovered a totally different culture, one we now call the CS culture. And these people, they don't use their fingers. Instead, they think their hands, well, they're good enough. This, however, gives them only 2 numbers. No hands equals 0, 1 hand equals 1, and 2 hands, well, 2 hands is the full set. So they have one full set with 0 left over, and that gives them 10. Comparing their culture to our own, it's quite simple to see that we have way more rules than they will ever have. If we use a simple trick proposed by Carl Gauss, you can easily find out we have 55 rules in total. The CS people, however, they have only 3. 0 plus 0 equals 0, 0 plus 1 equals 1, and 1 plus 1, well, that's the full set, so that's 10. And using these rules, we can also do addition in the system adopted by the CS people. Let's say we have 1, 1, and we want to add to that 1, 0. We just work from right to left, applying the rules as we go along. 1 plus 0 equals 1, we write it down. 1 plus 1, well, that's the full set, it's 10, so we write down the 1 to the left, the 0 right below. Final column is empty, so we get 1, 1 plus 1, 0, becoming 1, 0, 1. That's all there is to it. The CS culture, however, is not the only one deviating from our ways. There's also this other culture, and, well, they do really like using your fingers, but 55 rules is just too much for them. So they decided to do it slightly differently. No fingers again equals 0, however 2 fingers is now equal to a 1. And this kind of makes sense if instead of counting fingers, we're counting gaps between our fingers. So indeed, 2 fingers have 1 gap, 3 fingers have 2, 4 fingers have 3, etc. All the way up to a full set, which would have 8 gaps. But rather than writing down 8, this is called a full set, so we say it's 1 full set with 0 left over. If again we want to write down all the rules that we would need to use in addition here, we start out the same way we do. 0 plus 0 equaling 0, 0 plus 1 equaling 1, 0 plus 2 equaling 2, 0 plus 7 equaling 7, and then we get to 1 plus 1 equals 2, all the way up to the first very strange rule, which is 1 plus 7, because 1 plus 7 now suddenly equals a full set, so 1, 0. And finally, if we've written them all down, we get to the final rule, which is 7 plus 7. And 7 plus 7 is now equal to 1, 6. Doing addition with these rules is the same way we've seen it with our own system and with the CS system. Say we have, for instance, 254 and we want to add to that 167. We start all the way on the right with 4 plus 7. This now equals 13, so we write down the 1 a place to the left, the 3 below. We get 1 plus 5 plus 6 to equal 14, write down the 1 to the left and the 4 below, and finally 1 plus 2 plus 1 equals 4. And so there you have it. 254 plus 167 is 443. That's all there is to it. Now this culture, well, let's call them the gap way, because they use the gap between our fingers rather than our fingers themselves. But there's always some people who say, what? Why would you want less rules than 55? Why wouldn't you want a whole bunch more? Because after all, more is better, or so those people will proclaim. Well, someone thought, alright then, why not also use our toes? But it's kind of boring to just simply use our toes and our fingers then, so let's stick to this gap method. So we have 8 gaps as a maximum between our fingers, adding another 8 as a maximum between our toes, so we have 16 numbers in total. There's only one question though. How would I write 10 or 11 as a single character? Since traditionally we've always written them as 2. Well, there's an easy solution for this. The alphabet kicks in. So 10 is replaced with A, 11 is replaced with B, 12 is replaced with C, all the way up to 15, which is replaced with F. 16, however, the full set, would equal 1, 0. 1 full set with 0 left over. Again, the basic rules start out the same. 0 plus 0 equals 0, 0 plus 1 equals 1, all the way up to, in this case, 0 plus f equals f. Then we get to 1 plus 1 equals 2, 1 plus 2 equals 3, blah 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 blah, 1 plus f equaling a full set, 1, 0. All the way up to the final rule, f plus f equaling 1e. And, well, we've done this multiple times now, so it shouldn't come as no surprise that addition is just applying these simple rules multiple times in a row. Let's say, for instance, we have the number 38a and we want to add that to b1c. We start out at the right, a plus c. 8 plus c equals 1, 6. So we put down the 1 in one place to the left, we write down the 6 below, we get 1 plus 8 plus 1, which, well, it's no longer 10 now. Keep in mind that in this system that is a. So we write down a, and then finally we get to 3 plus b, and 3 plus b, well, that's b, and then we get c, d, e. E. So the answer must be e, a, 6. Now we also need to give this culture a name. Let's call it more is better, because these guys, well, they just want more and more rules, don't they? But now we've seen 4 methods of counting, and the question is, how are these in any way related? How can we go from one system to another? But before we take a look at converting them, let's start calling these by their proper names, shall we? And we shall do so using some Latin and a tiny bit of Greek. Starting with our own culture, which has 10 numbers, which we call the decimal system, from the Latin decem, meaning 10. Next, we examined the CS culture, which used a system consisting of 2 numbers. This we call the binary system, again from Latin bis, meaning dual or pair. Thirdly, we examined the gap culture, which used the gaps between our fingers and therefore resulted in an 8 numerical system. This system we call the octal system, again from Latin, where octo is 8. And finally we get to the one Greek one in our little collection of number systems here, which is the system with the 16 numbers, which we call hexadecimal. Hexa meaning 6, decimal meaning 10, and therefore hexadecimal meaning 16 numbers. Now that we've got the proper names introduced, let's take a look at conversion, shall we? So let's start with the most common conversion, and one you will be doing the most, if ever you're going to do anything with these numbers. It's binary to decimal. First, a small recap on what our own system actually does. Say we have the number 4123. The 3 represents the loose number of fingers we have, or the units. Then 2 is the number of full sets, or tens. 1 is the number of 100s, and 4 is the number of 1000s. So from right to left we have the number of 10 to the zeros, 10 to the 1s, 10 to the 2s, and finally 10 to the 3s, the 1s, the 10s, the 100s, and the 1000s. Now the same thing occurs when we take a look at the binary system. Only rather than using 10 as a base, we use 2 as a base. So the rightmost number represents the number of 2 to the zeros. The one to the left represents the number of 2 to the 1s. The number next to that, the number of 2 to the 2s, the number of 2 to the 3s, etc. So for instance, 1101 would represent 1 times 2 to the third, 1 times 2 to the second, and 1 times 2 to the 0th. So 8 plus 4 plus 1 equaling 13. Not, as it seems I've written here, 9. My apologies, that should definitely have been 13. But anyway, let's continue with the second example. We might as well take a somewhat larger number for the second example. So let's take 10, 110, 111, 001. Starting from the right, we can once again write in little script above the numbers these actually represent. So they represent 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and finally 1024. Now as we can see, the numbers 1024, 256, 128, 32, 16, 8, and 1 all have a 1 written below them. So all we need to do to convert this number is add these numbers together. Let's do that pairwise to keep things simple. So we get 1280, 160, 25 for a total of 1465. So converting numbers from binary to decimal is simply a matter of writing powers of 2 above them, seeing which ones have a 1 and adding those together. The reverse, however, is often said to be way more difficult. But rest assured, it really isn't, as long as you've got the powers of 2 remembered to a certain extent. Because in order to convert a number from decimal to binary, all we need to do is fit the largest power of 2 in there and continue doing this until we have nothing left. Let's say we have, for instance, 3184. The largest power of 2 we can fit in there is 2048. So we fit this 2048 in there, subtract it, and what we have left is 1136. We repeat the process, again fitting in the largest possible number we can, which is in this case 1024. 512 won't fit, so we can write down a 0. 256 won't fit either, so we'll put in another 0. And then 128. Well, 128 is still larger than 112, so I'm afraid that won't fit either, so another 0 it is. Then we get to 64, something that will easily fit. So we fit it in, write down a 1, subtract it from the 112 we had left, to have 48 left. 42 will definitely fit in there, so we repeat, we have 16 left, which will again fit, and then we have 0 left over. So 8, 4, 2 and 1 are not a necessity, and therefore we write down a 0 for these. One more? Why not? Let's do another one. 5,227. Well, again, fitting the largest power, which is in this case 4,096. What we have left over is 1,131. 2,048 ain't gonna fit, so we write down a 0. 1,024 will definitely fit, so we write down a 1. The leftovers is only 107, so 512, 256 and 128 won't fit in there, so we write down 3 zeros. Then 64 will definitely fit, 43 left, write down the 1, 32 will fit, so we have 11 left, write down another one, 11 left. 16 won't fit, write down the 0, 8 will definitely fit, so we write down a 1, 3 left, a 2 will definitely fit, 1 left, write down a 1, and 1 can be filled completely with another 1. 5,227 in the decimal system is equal to 101,000,110,111 in the binary system. To indicate what system we use, it's common to use this little subscript, if you will. So we can add a 2 to indicate that it's binary, or add a 10 to indicate that it's decimal. As it turns out, this most common conversion from binary to decimal or from decimal to binary is also the most difficult one. Binary to octal or binary to hexadecimal is very, very simple. As 8 is a power of 2, we can say that 0 to 7 can be represented in 3 binary digits, from 000 to 111. Therefore, if we have any binary number, all we need to do is group it in groups of 3 bits and convert every group to an octal digit. So let's say, for instance, we have 110, 110, 111, 101, 100, 010, 001. The way I just read this number already sort of grouped them. If we start all the way at the left or at the right, it doesn't really matter, but let's just start at the left. We see that 110 would equal a 6. The second 110 would also equal a 6. 111 would equal a 7, 101 would equal a 5, 100 is a 4, 1010 is a 2, and 001 is of course a 1. This large binary number can easily be converted into an octal number. All we have to do is group them, and we can easily see the answer is 6675421 in the octal system. For hexadecimal, the exact same thing goes. 16 is another power of 2, so 0 to F can be represented as 0000 to 1111 in binary. All we need to do now is, rather than group by 3 bits, we group by 4 bits. Let's say we have 0010, 0110, 1110, 1101, 1001, and 1111. These groups we convert one after the other to get 0010 equaling 2, 0110 equaling 6, 1101. It's kind of more tricky. It's 8 plus 4 plus 1, so that would make it 13, which is definitely not B, even though I'm going to write that down here right about now, but should instead be D. 1001 equals 9, and 1111 equals F. And then the correct answer should be 26D9F. The reverse is even simpler. Let's say that we want to go from octal to binary. So let's take the octal number 7326. All we need to do is take every octal digit and convert that into a group of 3 bits. So the 7 becomes 111, the 3 becomes 011, the 2 becomes 010, and the 6 becomes 110. Another example, 6271, 6 is 110, 2 is 010, 7 is 111, and 1 is 001. It really is that easy. The same goes for hexadecimal. AE21F would be A, well, A is 10, so 1010, E, which is 1110, 2, 0010, 1, 0001, and finally F, which is 4 ones. Now if we want to go from, let's say, octal to hexadecimal, the easiest way I find to do this is to simply go through binary. So 127, we first convert to binary to get 0, 0, 1, 0, 1, 0, 1, 1, 1, and then from that we go back to hexadecimal, starting at the end where we have a 0, 1, 1, 1, which would be a 7, then the next 4 would be 0, 1, 0, 1, and that's a 6, and finally the 0 in front, which is just a 0. So then we have 0, 6, 7 in the hexadecimal system. But these rules for addition will only get you so far. What if we wanted to do subtraction? Well, subtraction would lead to a whole new different problem. Because what would we do with negative numbers? We have used the minus sign for this, but as you might now have realized, the binary system, these zeros and ones that we have, they're the same zeros and ones that your computer uses when you hear people talk about bits or the zeros and ones that go inside computers. They're just this, a binary way of keeping track of numbers and characters. So if they only have zeros and ones, how would they represent negative numbers? Well, don't you worry, there is a solution for this, but it's a bit too complex to do in a minute, so you'll have to wait for my next video there.